Hello students, welcome to another lecture. So with today's lecture, hopefully we will complete the problem on cantilever retaining wall. So while you do that assignment which I given you, I will complete the full problem. So till now, on the two lectures that we have spent just for solving the problem, we had completed the proportioning part plus stability checks. So remember I told you stability checks are very important for retaining wall. So right now proportioning is done. Stability check means overturning and sliding the retaining wall is safe with the dimensions, and soil pressure also we had checked, that's also safe. Now let us proceed to the structural design of individual elements. So remember, when I discussed the theory, I told you retaining wall or cantilever retaining wall is essentially three cantilevering slabs, right? So you have the toe slab, you have the heel slab, and you have the vertical stem. So let us discuss all of those three elements separately and then we'll detail it. So first let us design the toe slab. Now for designing the toe slab, let us draw the pressure diagram. So remember in the last lecture, I'm just going back to the previous handwritten note. We had already arrived at the soil pressures 142.192 and 45.892. We had marked it here as well. So this pressure is linearly varying. So that is the pressure that I have here. Now what happens is, it is due to this soil pressure that these toe and heel slabs are bending. So that is the soil pressure. Now counteracting that pressure, you will have some pressure due to the sulfate of the toe slab. So that is what I have calculated it here. 0.62 is the thickness of toe slab into 25 is the sulfate of RCC. You will have 15.555, which is the pressure that is counteracting that. Now when I discussed the theory, I told you the soil sulfate at the toe slab will neglect it conservatively. One more reason you can think of, as I told you, is that during construction they'll dig the big hole, right? So during construction there will be a stage when this soil won't be there. But anyway, in any case, that we conservatively this sulfate of the soil will neglect, and also it is lesser in proportion to other stresses. Okay, so that's why here you have this is soil bearing pressure acting upwards, and for the toe slab you will only have this particular component, which is only the sulfate of the toe slab, nothing else, not the sulfate of the soil. Whereas when you come to the heel portion, you take everything. You take the height due to the soil, then you have to also take the sulfate of the heel portion plus surcharge effect also, that we take it as the equivalent height. So all of those things constitute the pressure at the heel portion. So you have an upward pressure due to soil and you have a downward pressure due to sulfate. So some of those will cancel out. So if I draw the line diagram, it will look something like this. At the top portion, the net stresses will be acting upwards. So see, whatever component you get here, you subtract it by 15.55, and this you subtract it by 15.55. This is the pressure diagram at the toe slab. At the heel slab portion, actually the upward force is more than the soil pressure. Remember, we discussed this during the theory as well. So that's also one of the reasons that you see the heel slab will bend like this, right? And tension is at the top because the force that's acting from top is greater than the soil pressure. So that is also seen here. So you subtract the respective ordinates, and this is the pressure diagram. Okay, so this is the pressures for which we will design the toe slab and heel slab. So now let us proceed. Now for the design of toe slab, we already discussed Remember, two-way shear is out of the equation because it's not like normal footings. You have to only deal with bending moment and shear force, which is essentially one-way shear. So again, when we discuss the theory, we discuss that for the toe slab, critical section for bending moment is the face of the wall, as always. Because see, you can imagine it's like a cantilever, right? So it's like trying to bend upwards. So this is the critical section for bending moment at the face of the wall, similar to what we also taken for footings at the face of the column, right? Now for one-way shear, it is at a distance of effective depth from the face of the wall. So that's exactly what I'm taking here. So for arriving at effective depth, I have to assume certain things. So total depth, it's already fixed. Clear cover is 75. Then bar dia, let's assume 16 dia. So you'll get the effective depth as 537. So bending moment and shear, we'll apply a factor of safety of 1.5, just like we do for footing design as well. So you can calculate the critical bending moment and critical shear. Now it is simple geometric calculation. So what you do is you can split it into a rectangle plus a triangle, and separately you can calculate the bending moment. So remember, bending moment is about this portion. So individually for this rectangle and triangle, you can take the lever arms at half and 2/3. And for shear force, you will calculate at the face at a distance of effective depth from the face. So effective depth is this. So at a distance of that, we will calculate the shear force. So both are calculated here. Now let us first proceed with the design for bending moment, because remember, for shear force, the shear capacity also depends on the percentage of reinforcement, right? So if we design first for bending moment, we'll get the reinforcement from which we can calculate the percentage of reinforcement. That will be helpful to check for shear. So for this bending moment, you calculate R mu by BD square. Similar steps you might have done this many times in DCS 1 and DCS 2. So I'm not going into details of that. So R equal to mu by BD square. So one thing you had to note here is that B in the case of retaining wall is always 1 meter, because we are designing per unit length of the wall. So you calculate R, calculate PT by 100 by this formula, you will get PT. So that is the percentage of reinforcement you have to provide. Now for that PT, you also check the shear force. So factored shear force is this. So shear stress is this. So for that particular PT, we can calculate the shear capacity, and it should be greater than the shear force, the shear stress that's already there. Now again, remember, for retaining wall there is no stirrups. So the shear capacity has to be met by the section itself. Okay, so this is the calculation. So for this PT, the shear capacity is also satisfied. Now I am not going to the shear capacity check again, but just for one time I'll just go there. So remember, this is our second. Yes, so this is our table. So for that PT, you can depending upon grade of concrete, you can calculate tau C, and that should be greater than actual shear stress that's coming. Okay, so that's it. So for shear it is safe. For bending you are getting this much PT. So for that PT you can calculate spacing. Remember, when we for calculating effective depth, we had assumed 16 dia bars. So you will get 1 dia of bar, right? And from that number of bars formula, you can get the spacing. So spacing is coming out to be 258.218 mm. You round it off to 250 mm, okay, to the lower side, so that it is conservative. So that is the design of toe portion or toe slab. Now you have to check for development length. So I have the clause open. So development length, you know that it is this formula. Now we are seeing that for 415 grade and the grade of concrete which we are using, the development length equation is 47 times bar dia. It is, we are seeing the same thing when we did the footings. So 47 times bar dia you will see it many places. So remember that it is strictly valid for 415 grade of steel and M20 grade of concrete. So you can check the development length for 47 times dia, 47 times 16, which is sin 52. So our actual length available is, see, this is 1.3 and the development length requirement is only 0.75 something. So along at this direction as well as this direction, there is sufficient development length, so it is okay. Again, the concept of development length, we will discuss it when we discuss the SP34 in the course of design of concrete structure drawing lab. Remember, we are doing those video tutorials, right? So I will discuss the concept of development length in detail there. Okay. Now let us design the heel slab. So for the heel slab, same philosophy, but the only difference that you have to note is, first of all, the bending is towards the other direction, tension is at the top, and as we discussed in the theory, critical section for bending moment is here itself, critical section for shear also it is here. Okay, so heel slab design is one of the rare cases where the critical section for shear is also at the face of the column or wall, whatever. Okay, we have discussed that elaborately when we discussed the theory, but in case any of you have any doubts, you can either go back to the theory lectures or you can refer to page 37 of IS 456. They are given it very with beautiful pictures and things like that. Okay, so again same procedure, but only difference, critical section of shear at the face of the support. So you calculate factored shear force, factored bending moment, again dividing this into rectangle and triangle. So once you get factored shear force and factored bending moment, exactly same procedure, you will calculate first design for bending moment so that shear design will be convenient. Calculate R PT by 100, then for that PT you calculate AST and spacing, and based on that PT you check for shear and we are getting it okay. Okay, so this design is also okay, the design of heel slab. So for the heel slab we are getting a reinforcement of 16 dia at 175 center to center. So for toe slab we had obtained 16 dia at 250 center to center. So more reinforcement is required in heel slab, and that is understandable because even though the overall stress appears to be low, the length is larger, so bending moment, shear force and all, or total force remains more than this. Okay, so we completed the design of heel slab and toe slab. Now let us go to the design of vertical stem. Now for the design of vertical stem, again the theory is same. So let me open some other handwritten note so that I can show you the full wall. Yeah, so for the vertical stem also what we said is the critical section for bending moment is this location, and critical section for shear is at a distance of effective depth. Okay, so already when we calculated the overturning moment, we had calculated the moment, but that is moment about the bottom of the base slab, but now you have to calculate the bending moment about this point. So there will be a reduction in the height that you have to consider. Similarly, to calculate shear force at a distance of effective depth, again you can use the active and the formulas that we use to check sliding, but the height is reduced. So when we check the sliding, we use the full height. So here you have to consider height of only this much, which is means you have to deduct the slab thickness plus effective depth. Okay, so that is clear. Now, yeah, that is what is mentioned here, the height of cantilever above base. And again, now we have to arrive at effective depth. So for effective depth, the total thickness of stem that we had already arrived at here, 0.65. From that, you subtract a clear cover of 50. Remember, we said for stem portion, we'll give a clear cover of only 50. Assume 20 dia bar. So this will be the clear cover. Then same procedure, but here you will be using the active earth pressure and surcharge. So calculation is similar as I told you what we use for overturning and sliding, but the height will change. Height will change not just for moment but for shear as well. Okay, so please take note of that. So again we will first design for bending moment, find out PT, AST and spacing. So we are finding out that we require 20 dia bar set, 175 centimeter spacing. Then with that PT, we will check for shear. So after you obtain factored shear force, we will calculate the actual shear stress, which should be lesser than that allowable for the percentage of reinforcement. Now, as a side note, I will also mention that here the bending moment and shear stress is not that much. So actually, we could have reduced the thickness of the stem portion a little bit for economy. But anyway, that's just a side note. Now, so that is the design of stem portion. So toe and heel slabs, they were shorter in length for in this particular problem. So we won't do the curtailment of bar, okay, but stem is very tall, right? So stem is 4 plus 1.25 minus 0.62. So for stem portion, maximum bending moment and shear force is here, and it will reduce as you go up. Theoretically, at the top there is no bending moment or shear force. Okay, so considering the height of the stem wall, we will curtail the bars that are going up. So what we will do is, see, the reinforcement what we got is 20 dia at 175 spacing, right? So that we will curtail after a certain height. That I'll show you when I detail the entire thing finally. Now, the another thing that I told about stem is that you have to provide minimum reinforcement in the perpendicular direction. That will take care of effect of temperature and shrinkage and things like that. Okay, and we will also provide nominal reinforcement vertically at the vertical side. So remember, whatever we calculated now, 20 dia at 175 cc, it is for this side, which is the tension phase. As in good detailing practice, since it is a bulky wall, we will provide nominal vertical reinforcement at the vertical face as well. So that also we will see. So temperature and shrinkage reinforcement is 0.12 percentage. So you have the cross section 650. Remember, 0.12 percentage of gross area. Okay. So this 0.12 percentage, again we are not taking it up from our head. It is given in the code. You can check up this clause. You might have seen that already for the case of slabs. It's a minimum reinforcement when you have HYSD. So what happens is, see, the entire section in the lateral direction is subjected to creep and shrinkage. So it is not good if we provide reinforcement only in one direction. So we have to only on one face. So we have to provide reinforcement along both faces. Now this face is exposed to the environment, which means it is more susceptible to temperature variations and things like that. So whatever total reinforcement that we are calculating, based on the minimum percentage of steel for creep and temperature and shrinkage. We'll provide it along both faces, and since this face is exposed, we'll provide 2/3 of the reinforcement along the exposed face and 1/3 of the reinforcement along the interior face. So that is exactly what I've done here. This is the AST. I multiplied that by 2/3. So this is the area of bar. So from AST, let us assume 8 dia bars. It is only nominal reinforcement. So assuming 8 dia bar, you can calculate the spacing. So it is coming to 96.66. I will round it off to lower value of 75 mm. So you are required to provide 8 dia bars at 75 mm. So remember, it is only 2/3. So it should be provided at the vertical face. Okay. So remaining 1/3 is at the inner face, which is a sloping face. So here you can double the spacing. So at the vertical face you are providing 175 mm. So at the sloping face you are providing 150 mm, because it is only 1/3 of this. So this is 2/3. Okay, on the vertical face, then on the sloping face it is only 1/3. So 150 mm. The spacing is double. Now you can curtail that, you can reduce that as you go up, because section is also reducing. So remember, this height is 4 meter, right? Now this is the full detailing. I'll discuss the other aspects later. First let me discuss this aspect. So 8 dia at 75 and 8 dia at 150, you will provide only up to a certain height. So this is 8 dia at 175, 8 dia at 150. Now that is last third of the height. To middle third of the height and upper third of the height, we will reduce the spacing. So from 8 dia at 150, we will provide 8 dia at 300 for middle third and 8 dia at 450 in the upper third. So similarly here also we will reduce 8 dia at 75 at lower third, 8 dia at 150 at middle third, and 8 dia at 225 at the upper third. So that is this minimum reinforcement. And also we said that at the vertical face we had to provide nominal reinforcement. So let us provide 10 dia at 300 center to center, 300 mm center to center on the vertical face. So that is this reinforcement. So this is the vertical reinforcement, 10 dia at 300 center to center. Now on the tension side, we had obtained a reinforcement of 20 dia at 175 cc. So that is this particular reinforcement, 20 dia at 175 cc. Now that also we can curtail. So bending moment and shear force are reducing as you go up. So once you reach the top, you can double the spacing. So alternate bars, when you curtail from this 175 spacing will double, and you will get 20 dia at 350 center to center. So these are the reinforcing detailing aspects. This is the width, this is the height, this is the depth of footing, thickness of toe slab and heel slab, shear key. Now vertical tension reinforcement should extend through shear key like this. This is the heel reinforcement at the top. This is the toe reinforcement at the bottom. Again we are providing nominal reinforcement in the other direction. That's what you are seeing these bullets, to take care of shrinkage, temperature and those effects. Okay. Now top reinforcement for toe, it is strictly not required because tension is at the bottom. Okay. For heel it is at the top. Okay. So this is the complete detailing of a cantilever retaining wall. So this completes the problem of cantilever retaining wall. If you have any doubts, please let me know. From next lecture onwards, I will start the problem of counterfort retaining wall. Thank you.